recording.
I wanted to ask a question.
And then get my screen turned around. I just asked, try to keep yourself muted unless you have a question. All right, any issues seeing the screen?
Nope, all good.
All right, perfect. That's what I want to hear. So like I said, tonight we're jumping into anatomy and physiology. We're going to cover some of the structures of the cells. We're going to talk, I try not to get real in depth with that stuff because even looking at the national curriculum, there's not a whole lot that they try to question you guys on when it comes to the National Registry. So I try not to go any more in depth than I need to. And to be honest, chapter 8 started out, right around 600-700 slides. By the time that I maxed the stuff up with the national curriculum, we're down to around 300. So I'm not going to throw anything at you that is not pertinent for you to know. And I'll be honest, in the back of the ambulance, a cell is the last thing I'm worrying about, or how the cell is functioning. Now, where there are some times that I might is when we talk about like fluid replacement and what types of fluid I might be using to replace volume loss in patients, or somebody that's maybe dehydrated. So there are the times, and again, I'll kind of hit home on those parts, and I'll try to talk about it a little bit more once we get to that point. So after the first slide, we're going to actually jump into our first two videos that I'm going to play, which is levels of organization of the cell, and then really what homeostasis is within our body. If I can get my PowerPoint, here we go. So anatomy is really the study of a structure. When we think of us as an organism, which is what we are, an organism is nothing but a bunch of organ systems put together. So we have our endocrine system, we have our neurologic system, we have our lymph system, we have our nervous system. We're a bunch of different systems to make up one organism. With inside those organ systems, we also have specific organs, such as the heart, such as the liver, but they're going to correspond to certain systems within the body. Now, physiology is really the study of functions or processes on the body, how those systems are going to operate. How does our endocrine system help regulate blood sugar? How does our nervous system help send and receive signals? That's really what physiology is. And we jump a little bit more into it in the next couple of weeks when we talk about pathophysiology and how the body reacts or changes to certain things. So thinking of organizational structure, almost like an organizational chart, if you will. It's kind of like how our body is. You know, our organism is us as a whole. That's us as a human being, as we are a living organism. Now, we make up, there are 6 units that make us up. We have chemicals, we have cells or cellular functions, tissues. Well, a whole bunch of tissues put together make up organs. A whole bunch of organs put together make up an organ system. And organ systems put together make up an organism. So you can really break us down or break down any sort of organism into different parts. Like I said, I'm going to pull up this first video. And if you guys are able to see this, let me know. All right, see, everybody's good with, they can see a video?
Nope, still looking at the PowerPoint.
All right, let's try. How about now?
Yep.
Perfect. Now, let me just make sure that I've got sound, and we're going to get going.
This video right here may be the most important video I make about anatomy and physiology. Why? The levels of organization that I'm going to share with you right here take you through the entire A&P course, the entire A&P everything. So with the levels of organization, what it is, the most simplest way I can tell you is it's the levels of the body. So if you're playing a video game, there's level 1, level 2, level 3, 4, and eventually it's the end. Okay? So in anatomy and physiology, this is your beginning and end of that game. The levels of organization starts down here and goes up here. So I'm going to just break them down for you and have some pearls here for you to remember. Okay, so here we go. You're going to see throughout the course of this video series here on anatomy and physiology. We're going to start with the atom, the smallest part, cells, tissues, organs, organ systems, the organism. Hey, that's us. So that's what we do. So the chemical level is the base level of the levels of organization. Okay, so chemical, or some may call it the molecular level. Okay, that's atoms. Okay, we then move up from there to the cellular level. Well, it's in the name. That's cells. Okay, from there we go to the tissue level. Now, what's a pro I can give you to remember tissues? Well, it's right above cells, right? So for tissues, think it's a bunch of cells working together for a common goal, to complete a common function. That's tissues. They come together. Cells come together. Okay? They're not separate. They come together and make tissue. Okay? Then we have organs. So now it gets pretty easy here. Okay? We know this kind of stuff. Organs, think of the heart. An organ system, think of how the body can maintain someone's blood pressure. What is that? Part of the cardiovascular system, right? Pretty cool, right? So we have blood vessels in that system. We have the heart. So the heart would be the organ, but the blood vessels and entire system at play is the cardiovascular system, okay? Now the final piece here we have is the organism. That's us, the human. There it is. This is the level of organization. I'll see you in the next video.
So very much like he said, I like to kind of hit home the fact that really when we talk about chemicals and tissues and tissues making up organ systems, I want you to think of like a blanket. Is a blanket just automatically become a blanket? What is a blanket made out of?
Cotton fibers.
Yeah, but it's a bunch of them put together, right? So that's really what our body is made of. It's a bunch of alike cells that come together for a common cause. And we think of cells, a whole bunch of cells get together, they make a tissue. A whole bunch of tissues get together, they make an organ. A whole bunch of organs get together, they make an organ system. A whole bunch of organ systems get together, they make us as an organism, as a living, breathing, functioning thing. That makes sense. That should be pretty easy to kind of understand. Now, some of the chemicals that are within inside of us, and some of the things that we can actually know a little bit about as a paramedic, if I can pick the slide right, water. Water is pretty important because we have patients that could have too much water, or we have patients that might not have enough. So in the case of having too much, this could be a patient, in congestive heart failure. Their lungs start to fill up with fluid, their extremities start to fill up with fluid. Or maybe it's a dehydrated patient due to illness, due to sickness, due to really environmental changes possibly. We have proteins inside the body. Proteins are going to give us energy. They're one of the building blocks that we need for our body to develop muscle. We have carbohydrates. Does anybody know what carbohydrates break down into?
Sugar.
Absolutely, it breaks down in sugar. In middle school science class, I remember our science teacher had us take a saltine cracker and put it in our mouth and just not chew it, just let it sit in your mouth and dissolve, which is like the hardest thing I think I've ever done in my life, because it's like putting a snack on a dog's nose and telling them not to eat it. But after 2-3 minutes, that saltine started to actually taste sweet. And it was because the carbohydrates were starting to break down into sugar. The two biggest things that our body needs to function is we need oxygen and we need sugar. So that's why carbs are very vital. It's another part of energy. It's another part of what a building block for us as human beings. We have lipids or fats. We have good fats and we have bad fats. Especially when we start to think of like cholesterol with people. We have HDL, LDL, and we start looking at changes that patients might need to make to their diets. Good fats would be like example of almonds or seeds, or some oils, as where bad fats are going to be processed foods, burgers or things we're going to get at a fast food restaurant. Nucleic acids. Is anybody in here really good at science? Of course not. We're going to be paramedics, right? So nucleic acids have a lot to do with, and the one, if I say it, it'll make a little bit more sense. DNA, RNA. are forms of nucleic acids. Now, DNA is really our genetic life form. It's a recipe that makes us as humans. A lot of it can be hereditary that we can pull from our parents, but it's what makes us unique. Salts. Why is salt important inside the body? What happens if I give a patient too much salt? What happens to the fluid within their body?
Water follows salt.
Water follows salt. So if I put a bunch of salt in somebody's body, guess what? They're going to retain water. They're going to become bloated. If I flush out all the salt out of their system, they're going to pee a lot more often. That's why people that maybe, eat or drink whatever it is that's really high in sodium, they tend to try to drink a lot of water afterwards because their body is thirsty. It has all that salt built up, and it's really thirsty for water. It's thirsty for some sort of liquid. That's why they always say if you're ever stranded in the ocean, don't drink the salt water, because the salt water will just keep making you more thirsty because the salt is looking to be quenched at that point. Some of the things this is broken down more in the category liquids, obviously fluids within the side of our body, gases such as carbon dioxide, oxygen, solids. We could even have solid organs, such as our spleen, such as our liver. Those are considered solid organs. Easy way to remember solid versus hollow organs. Hollow organs can rupture. Solid organs, you get a lac or you get a laceration to them. Your stomach can technically rupture. Your gallbladder, your lungs, those things are things that can technically rupture. As to where your spleen, your liver, they can't. They can get lacerated, but they can't just completely rupture. They're too solid for that. I try not to spend a whole lot of time on the atomic structures and atoms and chemicals because it's really not that pertinent in our education as a paramedic, and there's nothing on the National Registry for the new update that they even test you on any of this stuff. So I don't want to beat stuff into your head that is really going to just kind of sidetrack you, if anything. But atoms, if we break it down, are chemicals. Now, they consist of things called protons, things of neutrons, and electrons. I want you to remember proton starts with a P, so it carries a positive charge. An electron, well, we know it's electrical of some nature, carries a negative charge. Neutron, neutral, so the charge is unchanged. There's one organ system within inside of our body that conducts its own electricity, and that's going to be our cardiac system through a process called automaticity. So when we think of protons or neutrons or electrons, we're not necessarily referring to electricity, but we're referring to atoms, because every atom or every chemical will have a different makeup. It could have 2 protons and 1 electron, or 1 electron and 2 protons. So if I have 1 proton and 1 electron, the cell evens itself out. If I have 2 protons and 1 electron, I have a positively charged cell. If I have 2 electrons and 1 proton, I have a negatively charged cell. It's just like yin and yang. It's trying to balance itself out. When cells are perfectly balanced, they're stable. When they're maybe not balanced the best, they can potentially be unstable at that point. Now, let's think of a recipe when we talk about compounds. Say you're making pizza, or you're making lasagna, or I don't care, tater tot casserole, whatever it might be. That doesn't just poof appear out of nowhere, right? There are different ingredients that you have to get to collect that to make the final result, the final recipe that you want, right? And it's very much like anything else within inside of our body. Let's think of water, for example. What is the correct name for water? What's the chemical name for water?
H2O.
H2O, because there are 2 elements, hydrogen ions, and there's oxygen ions. Now, what's the 2 signify in H2O?
2 hydrogen.
Yeah, it's 2 tablespoons of hydrogen versus 1 tablespoon of oxygen. That's all it's saying, is that there's 2 parts hydrogen to the 1 part oxygen to make up water. When we talk about like the periodic table of elements, and each one of those is just going to be a substance in themselves, but you can combine them to make something else. Magnesium sulfate, sodium chloride, otherwise known as normal saline. it's just because, you know, it's sulfur or whatever else it might be, you can combine those to make different chemicals, just like a recipe, like we would at home if we were cooking something. A mineral within inside of our body is going to be something that is naturally occurring, inorganic. What we mean by that is, oh, let's see, I'm trying to think of a good example. Calcium, magnesium, those are minerals within inside of our body, but they're naturally occurring. Now, can I go buy those at the store? Yeah, sure I can. So they also can be produced synthetically as well. Now, there are, if you want to break them down even further, copper is technically one, iron is technically zinc. Although they are elements of the periodic table of elements, they are still naturally occurring in a mineral within inside of our body. When you think of, oh, I'm trying to give you guys a good example to not freak you out or anything like that. Chemical compounds of organic nature. Good example would be carbohydrates, proteins, fats, vitamins like A, B, C, K, E. If those connect with something else, they're what's called a biochemical compound. So if I combine carbohydrates with protein, okay, think of a recipe again. That's technically what they call a biochemical compound. Again, I would not try to memorize this. I wouldn't pay a whole lot of attention to it. It's just something that has to be covered. This is pretty important, especially because it deals with patients that we commonly see when we talk about patients that have low blood sugar or patients that have high blood sugar. Carbohydrates, right? Carbs break down into sugars. That's why generally we get a patient we give dextrose to. What do we try to have them eat afterwards? Or what do we try to have them drink afterwards?
Carbs or fat?
Yeah, carbs, right? We usually have them take a peanut butter jelly sandwich or drink some sort of juice. It's not the jelly and the peanut butter that we're trying to get into their system. It's more the carbs from those, more of the simple sugars that can be broke down. When we start to give patients like complex sugars, or what they call polysaccharides, that's more things like Coca-Cola or candy, because there's more than one form of sugar or more than one form of glucose within inside that itself. You know, candy has, I mean, if you look at the ingredients on a bag of Nerds or a box of Nerds, there's fructose, there's glucose, there's sucrose, there's all these different types of sugar. So they are polysaccharides, poly meaning multiple. Monosaccharides, examples are simple sugars, glucose, dextrose, fructose, so fruit juices, galactose. Now, galactose is going to be mainly found in dairy products, and it's pretty limited on how much is in dairy products, but like milk, cheeses, those are technically examples of galactose. But that's why we have a patient that, you know, we just pulled out of a diabetic coma, we gave them dextrose, we try to have them take carbohydrates afterwards. Why don't we want to give them something super high in sugar, such as candy or such as that Coke? Why would we not want to do that? What do you think happens to
Because you're
blood
gonna
sugar?
spike your,
Okay.
you're gonna spike your blood sugar too quickly,
Absolutely. So what happens when we spike?
And it's gonna drop really fast.
Bingo.
It's gonna drop too fast.
Any blood sugar that spikes quick will also drop quick. So we give it a simple sugar instead. We give it something as a carb, like a bread, like, you know, the jelly. Yeah, the jelly's a polysaccharide because it's pulled from multiple sources of sugar, but there are some simple sugars in it. We want their body to slowly break down the carb to maintain a blood sugar, not to just spike them right away, like dextrose does when we give it intravenously. Proteins, most abundant of the organic compounds that we will see in the body. Everything we eat, everything we bring into our body has protein of some sort to it, which is good because it really is needed by our body for energy. If we're sick, we pull from protein to fight off any sort of infection. We pull from it for any sort of allergens, as well as growth. You know, it says hormonal requirements. Those are even children that are growing. You know, there's a reason that we look for certain numbers of protein or a certain amount of protein in our diet. When you think of people that are like bodybuilders or really muscular, they up their protein because they're looking for excess amounts of collagen. They're looking for excess amounts of keratin because they want to build on top of the muscle mass that they already have. Fats, again, with inside the body, there's good fats and there's bad fats. When we talk about saturated fats or unsaturated fats, saturated is going to be more meats, eggs, milk, animal lard, oil, certain types of oils, coconut oil. As to where unsaturated is going to be things that aren't processed, nuts, seeds, plant oils, such as like olive oil. Those are going to be forms of unsaturated because they haven't been saturated with any sort of chemical. They haven't really been broken down at that point. Now, the good fats, great for our body. And again, eggs are usually pretty decent, but when we have a patient that potentially has cholesterol issues, they have to limit the amount of fats they bring into the body at that point. Does anybody know a medication right off the top of your head that we could commonly see in a patient that has cholesterol issues?
Statin.
Some sort of a statin, such as simvastatin, or you might hear the name Lipitor. Well, Lipitor and lipid, pretty close, but yeah, any sort of statin is generally to help with cholesterol. So if you have a patient that's on some sort of cholesterol med, what are we worried about inside their blood vessels happening? Especially, this could be a chest pain patient. What does that fat do when it starts to accumulate inside their blood vessels? It turns to plaque, and plaque turns to clots, and clots turn into a STEMI, or they turn into an aneurysm. So that's why we try to keep people's diet balanced, with well cholesterol or well balanced intake, so that we don't have that massive amount of fat floating around. That's why people that go out and eat 4 meals a day of nothing but fast food, that's why you've ever heard you're going to clog your artery or an artery clogging meal. It's because the amount of excess fat has to go somewhere. And a fear is that it's going to end up blocking a vessel. That's where that saying comes from. Nucleic acids, well, we need to know about them. We have DNA and we have RNA. If anybody remembers from the first Jurassic Park movie, when they were talking about how they make dinosaurs and how they essentially make them like little stem cell implants, the two classifications, DNA and RNA. Now, DNA is more, again, our genetic makeup. RNA is really just the messenger. We have messenger proteins that are going to follow out the orders of DNA, or send signals to DNA, or receive signals. DNA is really our code. It's what makes us what we are. It's our combination. RNA helps us get to that. That's set when we're born, and that DNA has to carry out functions. RNA is how it carries out that function. It's really just a messenger protein. Some of the inorganic compounds. So when we talk about inorganic compounds, as you can see, necessary for fluid balance, transporting materials throughout the cell membranes. That's great. Oxygen, carbon dioxide, salt, and water. We know that oxygen, we obviously need. We know carbon dioxide, we obviously need. Now, how do we truly measure oxygen? Because it's not through pulse ox. How else do we truly need to measure? If we want to look at somebody's partial pressure of oxygen, how is that performed? And it's usually not pre-hospital. It's done in the hospital. Anybody? Carbon dioxide would be the same as well. Usually through blood gases. You have an ABG done, arterial blood gas, and that's going to tell you the true partial pressure of oxygen that somebody has. It's going to tell you the partial pressure of carbon dioxide. We'll be able to look at somebody's sodium levels. And you can usually tell, especially for us, what we're going to be dealing with pre-hospital-wise, if you hear wet lung sounds in a patient, they're probably overloaded with fluid. Those are the patients that I'm not going to be giving fluid to. If I have a patient who has lower extremities that are swelling, again, not the patient that I'm probably going to be giving fluid to, because my fear at that point is that it's going to eventually start to back up into their lungs. But oxygen, carbon dioxide, salts, and water are technically considered inorganic compounds. Now, our body functions off salt a lot. We have something inside of our body called the sodium-potassium pump. And the sodium-potassium pump is really responsible for a lot of cardiac activity. It's what makes an electrical impulse. Electrolytes. So what are some common electrolytes that we could see inside the body? Somebody just give me a couple of them. Things that we could look at lab values of.
Potassium,
Okay, potassium's one. It's another one.
calcium, sodium.
Yeah, those are exactly what they are. Calcium, sodium, potassium. Yeah, those are naturally occurring electrolytes inside the body. But if somebody has low deficiencies of them, that's also something that we can give externally. You know, there are some services that carry calcium chloride, magnesium sulfate, potassium. Absolutely, we can tell if somebody's hypokalemic a lot of times by looking at 4 leads, by looking at 12 leads, which is something we'll go through next semester when we start to cover cardiology. Acids and bases. We know a little bit about the pH scale at this point. You know, 0 to 10, normal range for somebody at the pH range is 7.35 to 7.45. If I am below 7.35, am I an acid or a base?
Acid.
Yeah, absolutely, we're an acid. Think of dextrose, and I know I've said this before. Dextrose has a pH of 4.2. That's why it's very acidic to our blood vessels. Now, if I go above 7.45, I've got a base of some sort or some sort of alkali at that point. Now, if I have a patient that maybe is too acidic, another naturally occurring ion what's inside the body is sodium bicarb or bicarbonate. So that's why if we have a patient that has compartment syndrome or that has been in a prolonged cardiac arrest and we're worried about them being acidic, we can give bicarb to try to raise their pH level. All right, I'm going to play another video here real quick.
What exactly is homeostasis? Maybe you heard the word before, but you're maybe unsure what it means. There's some key terms here we got to know about when it comes to anatomy and physiology, when it comes to homeostasis. And it's one of the core things you have to know about. So here's homeostasis. Quite simply, it is the stable internal environment in the body. Now, that's the definition of it, okay? So if you see it on a test, that's what it is, okay? Now let's talk about how this all works. So throughout the body, you'll see the terms here. Let's just do the terms first. Homeostatic regulation, okay, is the umbrella term that involves all this down here. Receptor, control center, effector, negative feedback. We're going to talk about that. So let's start with the first one, okay? Homeostatic regulation. What that involves is the body's way of keeping itself in homeostasis using these principles down here, okay? Now, here's the first principle, the receptor. So there are receptors in the body, all throughout the body, and they're placed, and we're going to talk about later on in this course. There are receptors placed throughout the body that react to a change in the body or a stimulus in the body acted on that receptor. It picks up on it and then passes that information to that receptor's control center, okay? That control center then processes the information and then passes that on to the effector, okay? Which is going to basically take action on what's going on. Now, where every student gets messed up with these terms is negative feedback. All it means is the body's automatic response to any changes with homeostasis. That's negative feedback. To take action when things go awry automatically through the system right here that we talked about, okay? Watch this video over again until you have it down cold, and we're going to move on to the next video. What exactly is homeostasis?
All right, so our body has to maintain homeostasis. Somebody tell me what homeostasis is. If my body's trying to maintain homeostasis, what does that mean?
Balance.
I'm trying to maintain a balance within inside my body. Yin and yang, again, good and bad. So let's use this as an example. If my blood pressure drops, what does my body do in response to that? If I start to go into shock, what does my body start to do?
It attempts to compensate.
It tries to compensate. How does it do that?
Shunts blood to the primary organs.
Okay, so we shunt blood away from things that aren't pertinent, and we put blood towards things that are, such as primary organs. What else? How else does it try to compensate?
Heart rate will rise.
Okay, so
Try
our
to
heart rate
compensate.
increases because as these little sensors see, okay, there's a drop in our pool, we got to turn our pump on. We got to make our pump go faster to fill the pool back up. Our body is trying to maintain homeostasis when it's doing that. It's trying to maintain what is normal. Homeostasis is just our body at rest, and when our body is perfectly balanced, we don't have anything. That's a perfect blood pressure. That's a perfect heart rate. That's a perfect respiratory rate. That's just how our body functions. Now, when we start to get into like cells and cell physiology, there's some things that I want you to know about a cell. Obviously, a group of cells makes up tissue, right? Now, there's certain things that I'm going to mention here. I don't want you to, honestly, I could care less if you want to dive real deep into the cellular function or the anatomic layout of a cell. That's not my goal here. There are some things such as conductivity of cells. So if a bunch of cells that are like-minded get together, they can conduct an electrical impulse. That's what happens within our heart. That's how we look at an EKG. That's how we are able to get the heart to fire, is these cells all couple together and perform the same function. Now, cells can also reproduce. As life goes on, cells will die and new cells will be formed. Cells will also divide. They can make one into two. Does anybody remember think back to middle school, whatever it might be, what the brain center of a cell is?
Nuclei.
Yeah, the nucleus, right? That's really the think tank of a cell. That's where all functions are carried out from, is our nucleus. Now, a cell has an outer barrier. If you look at that, it kind of looks like a jellyfish on the outside. That is what's called our membrane. Now, cells can have permeable membranes. They can have semi-permeable membranes, meaning that if something's permeable, then something passes through it easily. It's kind of like running my hand underwater. There's no issue there. If something is semi-permeable, it's more like a sponge. There's still a barrier, but it can be absorbed. Think of our skin as semi-permeable. If I stick my hand under running water, does my hand absorb that water? No. Now, think as a kid when you went inside a bathtub. When you were in that bathtub for an extended period of time, what started happening to your hands and feet?
Gets wrinkly.
It gets wrinkly because we're absorbing that water. So we are technically considered semi-permeable. We have a barrier, but we can still absorb fluids. Cytoplasm is really what the cell is going to be. If you look inside a cell, there's fluid. It's, if we were to look at a cell under a microscope, you would see like all these little objects floating in something. That's what's called cytoplasm. That's just the fluid makeup of a cell. That's what makes it be able to carry the structures that you see within inside of a cell. Just think of it as almost like a gel-like substance. Two types of cells that we're going to see. So we have sex cells, which are going to be like reproductive cells. And then we have somatic, which is everything else. So sex cells are reproductive cells. Somatic is everything else. Kind of an easy way to remember it. Our membrane, again, think that jellyfish kind of structure to the outside of it, controls what gets in and out of it. Again, if it's permeable versus semi-permeable. Sometimes there could be an entryway to a cell where we have a process called diffusion or facilitated diffusion, where whatever's trying to enter the cell has to be the exact shape as the door to get in. If it's not, then it's not gonna be able to enter the cell. And I'll play a video on that here shortly. Cytoplasm, again, is our fluid in which the cell is gonna be composed of, where all of our structures are gonna essentially float in. Our nucleus contains our DNA. That contains the code for our life. It's literally, our body is made up of millions or billions of these little cells, and each one of these cells has a portion of our DNA or has our DNA encrypted into it so that it knows how it should function. It knows what it's supposed to do. It knows what its job is supposed to be at that point. When we talk about cells, we have the lifespan of a cell. So very much like us, there's a beginning and there's an end. So our 4 steps are our interphase, which is essentially the beginning of the cell, the life where the cell really just is starting out. The cell will then divide through a process called mitosis. The cell will then undergo what's called cytoplasmic division and then differentiate. Differentiate means the cell has to make itself different. Just something has to be unique about it compared to the other cells around it. Now, these cells, just like us, just like a plant, have to obtain nutrients. They need nutrients. They need sunlight, not literally sunlight, but like a plant. They need nutrients and things to be able to grow, kind of like us as humans as well. Again, we are made up of just a billion of these cells, so they function just like we do. The times that we're going to see cell division. So we've got meiosis. This is how egg cells in females are going to be reproduced, how sperm cells in males are going to be reproduced. We have mitosis, which is one I just mentioned here. This is when a cell decides to duplicate itself. It has to literally give up half of itself. It'll regrow, but it's dividing itself in half. This could be due to, let's think of leukemia for a second. Leukemia is a type of cancer in which the body has too many white blood cells. What's happening is that the cells are duplicating themselves more than they should. That's why patients with leukemia have a really high white blood cell count. Every cell is going to divide through mitosis besides reproductive cells, besides sperm, besides eggs. Those are going to undergo meiosis. So mitosis, all cells besides sex cells. And again, our cells have to be unique. Each cell has to be unique. Now, how do we make them unique? We can't, but it's made up within our DNA. Now, if cell division and growth outnumbers the amount of cells that are dying, that's when we start to get patients that have tumors or patients that start to have a mass of a tissue, is because the cells are reproducing a lot faster than they are essentially dying at that point. Let's see here. Let's take a 5-minute break. Come back at 6:45. We're gonna go through cellular signaling, respiration, and then we're gonna talk about how cells kind of move around. And then we'll hopefully get out of cells and into an organ. We'll get into the skeletal system. So take 5 minutes. We'll say 6:46 at this point, and then we'll come back and continue. All right, so cellular signaling. This is basically when cells are able to communicate with each other, when cells are able to talk to each other. So for cells to perform a common function, such as fighting off an infection or reproducing or just performing everyday functions like, grabbing a cup of water or, clicking the button on your TV remote. Cells have to work in conjunction with each other, and they do that through cellular signaling. That's how alike cells communicate with each other. This I would probably write down. Krebs cycle. So what Krebs cycle is it's the breakdown of sugar or glucose when either in the presence or absence of oxygen. So if you've ever heard of like aerobic metabolism or anaerobic metabolism, aerobic metabolism is when there is the presence of oxygen. Anaerobic is without the presence of oxygen. So our body can still use glucose with or without oxygen. The problem is it can only do it for so long if there is no oxygen with what we call anaerobic metabolism. Your body will exhaust itself pretty quickly, but it can be done. But again, you will wear out and tire out pretty quickly. ATP or adenosine triphosphate is what energy is. So whenever you see ATP, that's literally energy. ATP is how our body functions. It turns glucose and turns oxygen into ATP through the Krebs cycle. Us as humans, roughly 60%, you can see there, 60% of our body weight is made up of water. So when you think about that, I mean, literally you can change body weight of up to like 10 to 12 pounds in one day, just based off of water weight alone. That's why people that maybe are trying to lose weight will be self-conscious about how much sodium they're taking in. So of that total body weight, that's 60%, which is water, 63% of that water is intracellular fluid, where 37% of it is extracellular. So intracellular fluid means that our cells are going to be nice and plump, kind of like a glazed donut from Krispy Kreme. If they're not plump, then they are dehydrated. Our patients are then, kind of frail. They haven't eaten in a while, maybe kind of malnourished. Extracellular fluid is going to be when we have the patients that maybe have some form of edema. The fluid hasn't been absorbed by their cells. It's just kind of free floating. That's extracellular fluid. All right, let's look at cellular transport mechanism. How cells are transported, how things are transported inside and outside of cells. So again, if the membrane is permeable, it can be easily passed through. If it's semi-permeable, like a sponge, it can be passed through. It just takes a little bit more time. There are certain times with what we call something called diffusion, where something will move from an area of high concentration to an area of low. So if I have a really high concentration of something, it's going to try to move to something that has low concentration. Think of an hourglass. What happens when I tip an hourglass over? Well, the stuff with a high concentration naturally moves to the low side. That's technically a form of diffusion. When we go from high to low, it doesn't require any energy. Think of the hourglass. It does it just naturally. Filtration obviously is how our body, or mainly are going to be our kidneys, are going to filter out things through our body. Now, certain things that our body wants, it will trap certain nutrients, but it will flush the water out. Hence why we have to go pee a lot. Hence why the color of our urine can change. Let me play a video here real quick.
Diffusion is the movement of molecules from a higher concentration to a lower concentration, depicted right here. Higher concentration to a lower concentration. Okay, now here is some key notes we're going to go over on this. Now here's the first one. I'm going to read it to you. How does the ionar molecule move into the intracellular? Okay, there's how many? There's two ways that happens. Number one, it moves across the lipid portion of the membrane. The second one is passing through the channel protein in that membrane. So there's two ways it does that right there, okay? Now here's the last piece. So if I was to define osmosis, here it is here. It's the diffusion of water across the membrane, as you can see right there, okay? Now here, let's talk about the three solutions, okay? Now I'm gonna get out of the way, I'm gonna step in here, okay? So let's say we have a red blood cell, okay? And we have that red blood cell, when we put it in an isotonic solution, that means that everything is equal. Isotonic is another word for equal, okay? So the red blood cell stays the same, okay? It doesn't swell, it doesn't shrink. A hypotonic solution means there's more water in that solution. That's what that means, okay? So you can see here, there's a higher water concentration. With a hypertonic solution, there is a higher salt concentration. Higher salt concentration, hypertonic. So you're gonna get on your test. This is why I'm preaching all this. These are the buzzwords, like all these videos are, for your exams that you're gonna have on A&P. Isotonic, everything's equal. Hypertonic is when you're gonna see that red blood cell shrink up. Hypotonic, red blood cell's gonna swell up. There's what.
All right, I'm going to pause this for a second because I want to see if I can draw something. Okay, so isotonic. Let's just say I have 5 parts inside the cell. I give an isotonic fluid. I'm going to have 5 parts on the outside of the cell. It is perfectly balanced. There's no shift because it is, again, almost in a homeostatic state at that point. If I want to give a hypotonic solution, you can see right there next to RBC, it says swell. So it's going to make our blood cells swell. So it has a high water content. So let's draw our cell. And it has, I don't know, 3 parts sodium in it, or 4 parts sodium. But the fluid I'm giving doesn't have any sodium in it. Where's that fluid naturally going to go? It's going to follow the sodium, so it's going to make the cells swell. Now, if I give, let's say I have a cell that's full of water, maybe only has 1 part sodium. And now I give, let's say, normal saline, sodium chloride, and I fill the outside space with salt. The fluid from inside the cell is going to go outside because water follows salt. That's what he's referring to when he talks about isotonic, hypotonic, and hypertonic fluids. Let me get rid of my marks here. All right, so facilitated diffusion. If I look at this example right here, it's actually a pretty good example. Means that on the outside of my cell, I have these little channels. Why these little channels are important is because if I want something to enter the cell, it has to be that exact shape. So let's say I've got my cell here, and there's one entrance into my cell. And the inside of that entrance is circle shaped. Will a triangle fit in that circle? No, I have to have a protein that fits into that. That's what we're talking about, facilitated diffusion. It's literally helping it get from the outside into the inside. It's facilitating the entrance into the cell. And the site has to bind perfectly to the shape of the protein that's trying to pull in at that point, or the carrier. That's all facilitated diffusion is. Don't think any further into it than that. I know that's easier said than done. Now, when we talk about osmosis, this is literally the movement of water, nothing more than that. But it is a movement from low to high. So diffusion is from high to low. Osmosis is water from low to high. And how we do that is we accomplish it through the solutions that we give. Hypertonic versus isotonic versus hypotonic. So again, if I give a hypertonic solution, I'm going to make that cell shrink. This could be the case for a patient that we need to remove a bunch of fluid off of. That means we need to go to dialysis. We need to shrink their cells. If we have a cell that we want to puff up, this could be a dehydrated patient that we're giving fluid to. And it just depends on what type of fluid we're giving and what's going to happen to the cells or what's going to happen to the body at that point. Anytime we see any sort of facilitated movement, such as active transport or such as facilitated diffusion, which looks very similar, there has to be energy. There has to be ATP for it to function. It won't function. It doesn't happen naturally. Diffusion is the only one from high to low hourglass that happens without any sort of energy. Everything else is going to require energy at that point. If we're talking about moving things inside the cell, we're talking about endo for inner. If we're talking about moving things outside the cell, we are talking about exo. Exo is in exit, is the easiest way that I can put it for you. All right, we're through the hard stuff. So from here on, for the rest of the night, it should be relatively easy. Types of tissues that we are going to see with inside the body. So we've got epithelial tissues, which is really what covers our body surfaces. This is really going to be like skin. Connective tissues. This could be things such as ligaments, such as tendons that are literally going to connect things. Muscle tissues. Now, with inside muscle tissues, you've also got other categories such as cardiac muscle, smooth muscle, skeletal muscle. And then we have nervous tissues. And nervous tissues are really what's going to allow communication between our brain and our body. Our brain says, hey, I want to grab that glass. It's going to send a signal down our nervous tissue, and our hand is going to reach out and grab the glass at that point. So the first one, our epithelial tissues. Again, think skin. Think things that line our organs. It's really our first line of defense. It's really our first barrier before anything can enter any sort of structure that has epithelial tissue on the outside of it. Epithelial tissue is generally without any sort of blood vessels. It's really avascular. When we think of skin, we have the epidermis and the dermis. Our vasculature isn't in the outside of our skin. It's really down a little bit further by our sweat glands and our hair follicles. If we were to look at skin under a microscope, it almost looks like, depending on what type of epithelial tissue, if we're looking at like organs or if we're looking at skin itself, if you've never looked at skin under a microscope, it's kind of terrifying. It looks like the Grand Canyon. It looks like it's just full of cracks. It's dry. It looks like a desert, to be honest. Our connective tissues, again, think of things that are going to connect bone to bone, things that are going to connect bone to muscle. They're also going to be responsible for creating framework, giving us structure, giving something structure. It could repair damaged tissues. It could hold fluid. You know, we talk about specialized cells, extracellular fibers, ground substance. These are the components that make up connective tissues. Different types of connective tissue, if you want to dive into it even further. So if we look at tissue fiber type towards the bottom, so we've got like collagen, bind structures with high strength, kind of what collagen does. Elastic, it's going to help us with stretching, so we might see that more in our tendons or ligaments. Reticular, that is very much, if we think of like a reticular activating system within our eyes, it's really just a support network for our senses at that point. I'm not going to dive into this more than I need to, but some of the dense connective tissues we can see, tendons, eyeballs, deep layers of our skin. Loose tissues could be like fat. Muscle would be another dense connective tissue technically. Loose connective tissue is really just kind of sitting there hanging out at that point. Connective tissue that's supportive, cartilage, bone. Bone is very much a tissue. It's just a bunch of layers of it, kind of like an onion if you've ever seen Shrek before. Now, with bone, there are technically blood vessels that run in bone. That's actually where production of red blood cells happen. That's where the production of white blood cells happen. That's where the production of platelets happens. So patients that have osteoporosis, that maybe have a breakdown of bone material, might have lower blood counts just because their bones are a lot weaker. Your muscle tissues, this is pretty important to know, the 3 different types of muscle tissues that we'll see. Skeletal muscles. So that's really going to be what's going to sit on the outside of our skeletons, our bicep, our tricep, our calves, our quads, the muscle that you think of when you see somebody standing. If somebody was standing there anatomically and you can see muscles, that's what you're looking at as far as skeletal muscles. Now, smooth muscles could be blood vessels, could be intestines, could be let's think of another one. Your esophagus. That's technically a smooth muscle. They aid with digestion. They aid with blood supply. And then cardiac muscle is going to be literally the muscle within inside of our heart that has electricity to it. Involuntary, we can't control it, but it is technically a muscle. Our nervous tissues, again, it's going to send signals to and from. It's going to send signals to and from our muscles. It's going to send signals to and from glands. It's also going to receive information. So as I touch things, as I look at things, as I smell things, signals are going back to my brain through nervous tissues. They are essentially little messenger cells. They perform and carry out functions, and they tell the brain what I'm seeing. If I look around my office and I see pictures or something like that, it's sending signals back to my brain so my brain can correlate what I'm looking at. That's what our nervous tissue is doing. It's really just communication pathway at that point. Some of the types of membranes that we're going to see. So a membrane is really going to be the outer layers of something. We've got our serous membrane, which is going to really line like body cavities. I'm trying to think of a good example of this, like your chest wall, your abdominal wall. There is no opening to the outside, so this serous layer lines those cavities. We have our mucous membrane, which is going to be kind of like what we would have under our tongues, kind of like what we have in our nose. This is what's going to absorb medications if we give it intranasally or we give a medication sublingually. Cutaneous should go without saying, like a subcutaneous injection. So cutaneous is going to be skin. And then we have a synovial membrane. Now, synovial membranes are exclusive to joints. They're gonna be what's covering joints. Usually it's to assist with the movement of bones, because again, when we move, it's not bone on bone. We do have some sort of cushion there that allows us to be able to not have excruciating pain anytime we move 2 bones together. Homeostasis, I think I covered this a little bit. Homeostasis actually is derived from a Greek word, means same, steady, like steady. So that is our same and steady state. That's when our body is most ready for whatever at that point. That's when it's most likely to react to something, is when we're at a level of homeostasis. So our body maintains homeostasis through things such as compensation that we talked about. What happens to our body when we get really hot? What does our body do?
We sweat.
We sweat, right? The body's trying to naturally cool itself down. What happens when we get really cold?
We get goosebumps.
We get goosebumps or we shiver. Shivering is our body trying to warm itself up. That is our body trying to maintain homeostasis at that point. How we try to maintain our pH system. Well, if my carbon dioxide levels are up, my body tries to blow it off. It'll try to get rid of excess acid through urination. Our body is really just trying to maintain this balance of homeostasis. When we have too much salt, our body gets thirsty. It's trying to balance itself out. And compensation is the best word for it, whoever said that earlier. Cells are going to get older. And again, cells are going to die, very much like us. So what happens is these cells, as they get older, we have what's called cell turnover. So new cells are produced, the older cells essentially pick off. And this is just a cycle that keeps on occurring. Older cells will cease to exist, newer cells will take its place. Our body does that to maintain homeostasis. Otherwise, our body wouldn't be able to function like it would. We'd be a lot slower. We wouldn't be able to almost think of an elderly person. I hate to be that way, but that's how our cells would be. Now, our body doesn't try to fight itself, but there are countermeasures to everything our body does. So let's think of, again, if my temperature rises, my body releases sweat. It tries to essentially fight itself. Instead of just lowering our temperature, which our body can essentially do, it has a mechanism to try to do it instead. It has a fail-safe. How our body tries to eliminate heat. So convection, anybody that's in the fire service or on a fire department or anything like that, this should be nothing new to you. We have convection, conduction, radiation, evaporation, and respiration. Somebody give me an example of convection to cool a body down. How does that do that? How does that work? Or what's an example of it? Or think of like a convection oven.
The air around is like the AC in the house.
Yeah, it's air movement generally. That's what a convection oven does. Heat, and then it moves that heated air around. What about conduction?
Direct contact.
Yeah, direct contact, the D for direct. Radiation.
Indirect contact.
Okay, indirect contact, kind of like a sunburn. Evaporation, good example. If I put a pot of boiling water on the stove and I forget it's there, what happens to the water eventually? It's gone, right? And then I start to smell a burning smell. I'm not going to say I didn't do that 3 nights ago, but that's what reminded me of it. And then respiration, as our body increases in heat, it tries to blow off that excess heat through our respiratory system. So our body, when we are trying to balance input and output, it takes in nutrients as we eat, as we drink, whatever it wants. Our body robs what it wants out of the liquids, out of the solids. And then the rest is essentially excreted through our system, through sweating, through breathing, through urination, through defecation. It takes what it needs. It takes the sugars, it takes the proteins, it takes the oxygen. And anything excess at that point is just pushed out of our body. It filtered out and pushed out. So now we're not covering any organ systems, anatomy and physiology, because that's literally what next semester is all about, is disease processes of each organ system. So the cardiac system, the circulatory system, the nervous system, our GI system, our GU system, our skin, our renal system. Literally, those are all things that we cover next semester, and disease processes in regards to them. So I moved, literally, I took slides and just moved them to the PowerPoints for next semester. Integumentary system, so skin. Again, first line of defense, protects the body. Also protects us for cold environments or from hot environments. Tries to regulate fluid. Tries to give us some level of protection when we talk about inflammatory responses. So you injure your arm. It turns red, you get a bruise, and it might swell up a little bit. That's an inflammatory response by your body. It's literally sending a massive amount of red blood cells to that area to try and fight whatever's going on. And skin is also going to give us some form of sensation. You know, if I go to touch something, I'm be able to feel it. And my body sends the signals through my nervous system back to my brain to understand what I'm feeling at that point. Now, our skin system is also going to house our hair. It's going to house our nails, oil glands, sweat glands, things that we need to function and help us with temperature regulation. Any sort of orifice or opening is generally lined with a mucous membrane. So think of your mouth, think of your nose, think of your ears, think of your eyes. Those are technically all mucous membranes. You know, you can have a runny nose, you can have dry mouth, you can have tears coming out of your eyes, you have earwax. Those are all forms of mucus technically. All of them are also ways that we can receive medication, eardrops, eye drops, intranasal medications, oral medications. So anytime we have any sort of opening, generally it is considered a mucus orifice or something that is going to be lined with mucus. Now, our skin is actually the largest organ that we have, believe it or not. The two layers of the skin, epidermis, which is going to be our outside layer, and then our dermis, which is going to be a little bit deeper. And then we have our subcutaneous tissue or adipose tissue. It's going to be largely composed of fat. So if I was to put a diagram up, our epidermis, again, is really just the uppermost layer. Our dermis is going to house our sweat glands, our blood vessels, our hair follicles. And then underneath that, we're going to have our fatty tissue. That's really where, when we think of a subcutaneous injection, that's the site that we're going for with those specifically. I guess I just went ahead of myself and started talking about this already. In regards to our subcutaneous tissue, we have our fascia, which is kind of the thinner layer of fat. And then we have a deep fascia, which is going to be a little bit thicker. And that's really where we're trying to get medications out. It's more fibrous as opposed to normal fascia, which is going to be more of like connective tissue. It's going to have, I'm trying to think. Some blood vessels, some hair follicle roots still, as we're deep fascia is really going to be muscles and bones are right underneath that. Our skeletal system, I would start to write some stuff down if you haven't already, or start take pictures at this point. 206 bones in our body. What our skeletal system does is it provides a framework for us. It gives us structure. It gives us some sort of symmetry. If you look at us, literally, we should be symmetrical. Our bones should match the bones on the other side. It also gives us protection. When we think of our rib cage or we think of our spine, those are protecting organs. Our spine is nothing, or our vertebrae is nothing more than protection for our spinal cord. That's what our concern is when somebody breaks their back. It's not that they broke a vertebrae or slipped a disc. It's that we're fearful for some sort of spinal cord injury at that point. Now, technically, the bone is a means of access. It also stores things, hence why we do intraosseous infusions. If bones, patients can have certain conditions such as osteoporosis, which they will probably have a lack of calcium at that point, that doesn't allow their bones to be as strong as they should be. And again, our blood cells are going to be produced inside of our bone. That's why we will still get blood return when we do an IO. Is because that's where white blood cells, that's where red blood cells are produced. Now, when I talk about an axial skeleton versus an appendicular skeleton, axial means things that are generally running up and down. So we have our skull, our rib cage, and our spinal cord, or our vertebral column, which protects our spinal cord. When we talk about appendicular, it's anything running side to side. So our shoulders, our pelvis, our upper and lower extremities. These are things that are going to be symmetrical on one side versus the other. So when we're assessing patients that potentially have a skeletal injury or broken bone, that's why we're feeling one side versus the other. We're checking for symmetry at that point. Now we have cartilage, we have tendons, we have ligaments. So cartilage is really going to cover the end of bones where joints are. It gives us that cushion so that we don't have bone on bone. A tendon is going to connect muscle to bone. It's what holds muscles to bone. So if we, have a torn tendon, we could have a muscle that's displaced, as to where a ligament is going to connect bone to bone. It's almost like a rubber band at that point. Some of our common long bones. So our humerus, our upper bone of our massive bone of our upper arm. We go for the humeral head anytime we're looking for an IO there. Our radius and our ulna in our lower arm. Remember, the radius is always the side of your thumb. Your ulna is always pinky side. Femurs, we should know what femurs are. Tibia and fibia. Now, long bones are going to have a shaft, which is also called a diaphysis. The shaft itself is called the diaphysis. and then two ends that have joints connected to them. So think of our joint at our wrist, our elbow, and then our shoulder. Those are all joints. Now our lower leg, we have our pelvis, our knees, and then our ankles. So there are joints at either end of our long bones. Short bones, fingers, toes, bones with inside the wrist, bones with inside the hand themselves, really for fine motor movement or fine sensation. Flat bones, skull, ribs are going to be technically flat. Our shoulder blades are flat. Irregular facial bones that just have no reason why they are besides maybe to give structure. Vertebrae are technically considered irregular as well. But again, the vertebrae have the job of protecting our spinal cord. Our pelvis is technically irregular because it has parts that are flat and it has parts that are irregular in shape in itself. But again, most of these irregular bones are protecting something. So facial bones are generally protecting underneath our sinus cavities. Vertebrae are protecting our spinal cord. Pelvis is protecting blood vessels that are running along our legs. Now, I don't expect you to memorize all the bones. I did put some worksheets up on Canvas. I'm sure maybe you got notifications for them. One is of facial and head bones, and the other one is of the skeletal system. So what I want you to do for those assignments is just label them. That's all I'm wanting, is label the bones. When it's done, send them to me in an email, and I'll give you a grade for it. Compact bone is just as it sounds, really compacted, really hard, as opposed to cancellous bone, which is more spongy. This is going to be inside bone itself. It's almost, again, like a spongy area. So when we do an IO, we're generally drilling through that part, your spongy bone. Here is an example of your long bone. As you can see, I was saying that our shaft is called the diaphysis. We have our metaphysis, which is the upper head of it. And we have our epiphysis, which is the lower head. Now, even though our bones begin to form as we're small little human beings inside of our moms, our bones are not, what's the word I'm looking for, as hard as they should be. They're very pliable, and our bones aren't even fully developed when we're born. If you think of kids, what do they usually have on top of their head when they're born?
Soft spots.
Yeah, soft spots, a fontanelle, because their skull isn't totally formed at that point. There's a reason that kids, when they break their bones, and an older person, if they break their bone, it literally can splinter or shatter. Kids, they call them green stick fractures. Think of a stick. If you have a stick that's been laying in your yard for 2-3 months and you go to bend it in half, it snaps. Think of a stick you just pull off a tree that's very much alive. It wants to bend before it snaps. That's why they're called green stick fractures. Kids are very, very resilient. It takes a lot of pressure, or the right amount of pressure, or the right amount of twisting to cause a injury in kids. And what we're concerned about, especially while they're growing, is any sort of growth plate issues, or if they've injured a growth plate. We can't tell that in the field, but that's usually done during X-ray. Two classifications of how bones are formed. I wouldn't remember this, but endochondral ossification is the process of bone formation when we are about that small. As where intramembranous ossification is the formation of flat bones, such as our pelvis, such as our shoulder blades. There's our growth plates that I was just talking about, that as we grow, these growth plates act as essentially a little fertilized area that will allow the bones to expand. It will soak up a whole bunch of nutrients. It will help with growth. It'll help with repair. It'll help with hormone replacement. And again, a lot of this is pulled from the amount of nutrients that we eat as adolescents. That's why we had to eat our vegetables. That's why we had to drink a bunch of milk, is because those nutrients really help our growth plates and allow us to become big and strong like our parents said they did. All right, let's take 5 minutes again. We've got like 30 slides left after that. So we'll say 7:26 and then we'll finish off our slides. All right, jumping back into joints. So joints are going to allow movement of extremities. Think of like your knees, think of your ankles, your wrists, your elbows, your shoulders. Now, joints are formed at where two long bones meet. So where my radius and ulna meet my humerus, I will have a joint such as my elbow. Now, whether they are a movable joint versus an immovable joint, or they only move in one position, like our elbow, we can't technically, I know some people can, maybe you're double jointed, you can flex your arm backwards, it freaks you out, but they're going to be classified as either immovable joints, slightly movable joints, or freely movable. Just kind of depends on location, and it depends on the person, because again, some people are double jointed and can move things in ways that other people aren't really going to be able to. So when we look at joints, it's going to allow your bones to pivot in the way that we need to. You can see like this little cushion here in between the two long bones. It's going to allow those bones to essentially swivel back and forth without having any sort of grinding or any sort of pain. When that starts to break down, that's when our patients maybe have developed something such as arthritis, where they just don't have the movement in their joints like they used to. Or they had carpal tunnel or something like that, where we have a breakdown of those joints and it's causing extreme pain. If you want to look at the joints all throughout the body, perfect, that's great. There's 230 of them in the human body. I don't expect you to know joints by any means, but how some of the joints might function. So our jaw is essentially a pivot joint, right? It pivots on, it's like a hinge. Our shoulders, our ball and sockets, our knees, our elbows, those are technically hinge joints. Our wrists, technically saddle joints. Ones I'd say remember is your hinge joints, your ball and socket, your pivots. Those are the big ones, in my opinion. Again, there is a sac or like fluid, synovial fluid, that is going to be inside the joint itself that gives it cushion. So anytime we refer to that substance or that liquid, we're referring to synovial fluid. It's also going to assist with fighting infection, removal of any debris, and again, give it more of a cushion when we need to move two bones in either a direction that is favored or one that is unfavored, as you're going to have that synovial joint or synovial fluid. Our axial skeleton, remember, runs up and down. Skull, thoracic cage, and our vertebrae within our back. Now, their main job is to literally protect the spinal cord. We have our brain and our spinal cord, which makes up our nervous system. That's really it. And the main job of these is to protect that. Now, our thoracic cage also protects our heart, it protects our lungs, but the skull and the vertebral column, or our vertebrae in our back, are there to protect our spinal cord. Now, our skull is made up of a whole bunch of different bones. And again, I put a worksheet on Canvas for you guys to complete. If you want to use this PowerPoint to do that, you can. If you want to look in your book, I don't care. It is held together at these joint sites. If you can see those little cracks inside your skull, those are called sutures. That's where different parts of the bone are held together, different parts of the skull are held together. Now, when somebody undergoes a skull fracture or some sort of broken part of their skull, it takes a ton of pressure to actually crack your cranium. I'm not talking facial bones, I'm talking the hard part of our head, our frontal bone, our occipital bone, which is the back, our temporal bones, which runs on our side. Your skull is actually super thick because of what it houses and what it protects. Skull itself, 28 bones within 3 groups, such as your cranium, your facial bones, and then you've got your vertebral bones, which at the bottom of your skull, we have a hole. What do you think goes through that hole at the bottom of your skull? If I was to pull that up, what goes in that hole?
Nerves.
No, it's a big nerve. Brainstem and what? What's past our brainstem?
Spinal cord.
Spinal cord. Okay, that's what I'm going for. That hole is what we call a foramen magnum. If you look on the right side there, Now, the problem is when we got patients that have some sort of rising intracranial pressure, maybe due to a head injury, maybe due to some sort of infection, maybe meningitis, whatever it might be. Our concern isn't the pressure itself. Our concern is that the pressure is pushing the brain and the brain is trying to exit out of that hole. The other issue is our brainstem houses a lot of the functions that we just normally do, breathing, maintaining blood pressure. Those are all housed within inside of our brainstem. So if we put pressure on that brainstem, because again, it's trying to exit out of that hole, we can see patients become unable to breathe. We can see patients unable to maintain their blood pressure just because of rising intracranial pressure. I don't expect you to memorize any of these bones at all. These ones more so on the left-hand side. Nasal bones are zygomatic bones for our cheeks, our maxilla bone for our upper lip, our mandible, the frontal bone, the occipital bone for the back of your head, your temporal bones on either side. Those are ones that I would expect you to look into. I don't, you will not, there's no way that you're going to memorize all these. But even our skull, if you look at it, it's pretty symmetrical, one side versus the other. Our body is all about symmetry. Our neck, pretty much supported by our vertebrae. Our neck houses some important things such as our trachea, such as our esophagus. Now, when we refer to like carotid arteries and jugular veins and nerves, a lot of people, when I talk about like doing performing an EJ on somebody, your arteries are really kind of tucked away behind muscle. You would really have to try to hit an artery. As to where your external jugular veins are really going to run on the outside of your neck, kind of like where the labeling is, where it says thyroid or where it says carotid arteries. That's where your jugular veins are going to run. I'm not too worried about the vein because the vein is under low pressure. Also in the middle of your neck, something that's important, you have your trachea. What is that small little area, that cricothyroid membrane? What do we use that for?
Airway access.
Airway access. If we have to cric somebody, that's the area that we're shooting for at that point. Absolutely. Now, this is super important. The vertebrae inside of our back. We have a certain number of each type of vertebrae. So our cervical vertebrae. So within our neck itself, we have 7 vertebrae. Our chest, back, we have thoracic, we have 12. Our lumbar region, which is where most back injuries occur, we have 5. Our sacrum, which is part of our tailbone, we have 5, and our coccyx, which is the end of our tailbone, we have 4. How I remembered it, because I can remember numbers for some reason, is I always said 7, 12, 5, 5, 4. That's just how I remembered it. Like a combination, 7, 12, 5, 5, 4. Because I knew where cervical was, C-collar, thoracic, rib cage, lumbar, mid-back, sacrum, and coccyx tailbone. I remember the numbers, and that helped me out. Now, why these are important is, say that we have a patient that gets in a bad accident and they've got an injury right around the level of T4. Why is that significant, you think, if they have a spinal cord injury at that level? Is there a potential that anything underneath that is no longer going to work? That the patient could be paralyzed? Yeah, if they have a spinal cord injury there, we're not worried about the vertebrae themselves. Those will heal. There's discs in between the vertebrae. I'm not worried about those. What I'm worried about is the spinal cord that's within it. If somebody gets a severe enough fracture at the level of T4, they can lose the ability to breathe. They lose the sensation. The body isn't able to receive or send signals below that level, so that the patient could potentially be on a ventilator at that point. Not because they don't want to breathe, because their body just doesn't have the ability to anymore. They've lost the channel that their body between their brain and their lungs. Or if somebody gets, lower, maybe at T10, that could be lower extremity paralysis. So most of the injuries that we're super concerned about are going to be right here in the thoracic region. Now, again, we have discs in between them. You may have heard somebody say they slipped a disc or whatever it might be. It's a little cushion in between our vertebrae. Now, if that disc disintegrates, they can undergo what's called a spinal fusion. And what that does is essentially fuses two vertebrae together so they can no longer bend. They can no longer move. It keeps them in one position. It prevents them from flexing. Now, our vertebral column is also going to give us posture. Depending on how poor our posture is, could depend on how out of alignment our vertebral column is. Our chest, again, rib cages, ribs themselves. In between our ribs, in those empty gaps, we have what's called intercostal spaces. Those are the spaces that run in between our rib cage, or in between our ribs themselves. But it's important because it houses some of the most important organs that we have: our heart, our lungs, our great vessels such as our aorta. Really, our rib cage is there to protect us. The way we are designed is really everything is to protect something. If we think of skin, we think of muscles, we think of tissue, we think of bones. Everything is just another layer of protection within inside of us. It is also going to house our diaphragm, which is going to allow us to bring air in when we breathe. It's going to push air out when we exhale. Now, when it comes to some of these, let me actually just pull them up. It's going to be easier to. Thoracic vertebrae, 12 pairs of ribs, our xiphoid process, our manubrium. Looking at our thorax, if I was going to do some sort of procedure that, such as to release air from somebody's lungs, a needle decompression, the point that I would do that at is right here, the second intercostal space above my third rib. I don't go underneath the rib because there's blood vessels that run under each one of these. So I try to go above it. So if I go on top of the third rib, I know I'm not going to hit any blood vessels. But the point for needle decompression is your second intercostal space, mid-clavicular line. So what I mean by mid-clavicular is if you find your clavicle and draw a line straight down it, that's the area that I should be performing decompression at. Now, why do we perform them up high? It's because we're trying to release air. A lot of the times they put chest tubes in down low because they're trying to get rid of fluid. And then you can look at our ribs on the back here, our 12 pairs, our scapula or our shoulder blades on either side. Down here on the front, we have our xiphoid process, which is kind of the pointy part of our sternum, the very end of our sternum. We have to be, when we teach CPR, we teach somebody BLS, we tell them not to put their hands too low because you can essentially snap that part off. We want to keep their hands on the patient's sternum, not on the xiphoid process. If you look on the back, 11 and 12 are what are considered free-floating ribs. They're not connected to anything. They are the only ribs that are considered free-floating. But again, vasculature, nerves, everything is going to run on the underside of each one of our ribs. Our appendicular skeleton running side to side, shoulders, pelvis, upper extremities, lower extremities. It's literally everything running side to side besides our rib cage. Rib cage is in our axial skeleton. And again, how we determine if there's an injury of one of these is through symmetry. We assess these patients, we feel one side versus the other. I don't expect you to know every single one of these bones. I expect you to know the basic bones. What is a clavicle? Okay, what is a shoulder blade or scapulae? What's a humerus? I don't expect you to know what a supraspinous fossa is. That's not anything that you'll be questioned on. They won't go that fine into detail. But you can see here we've got an example of a ball and socket joint right there at our humeral head, where it meets up to our scapula. Our upper extremities. So we've got our humerus up top. We've got our radius, which again is going to be thumb side. We've got our ulna, which is going to be pinky side. Makes sense because we take a radial pulse on the thumb side. We have our bicep, which is going to be on the top part of our arm. We have our tricep, which is going to be on the bottom side of our arm. When we look at hands, so phalanges are literally from the bottom of your finger to the tip are considered phalanges. Now, the hand bones from your hand to your wrist are considered metacarpals. And then any bones inside the wrist themselves before you get to your forearm are considered carpals. So we have carpals, metacarpals, and then phalanges. What is a concern if somebody has a pelvic injury? I mean, think bleeding. How much blood do you think could hide in the pelvis? Just take a guess.
Couple liters.
3 to 4 technically, really. So yeah, it's a lot of blood. And you'll notice a difference here between males and females. Females' pelvic girdle is a little bit different than males, just for childbirthing reasons. Is the big thing, is the big difference here. But yeah, your pelvis can hide a massive amount of blood. So it's always a concern if we have somebody on blood thinners that potentially has a pelvis that's unstable. Our pelvis serves very much as a trunk, kind of like a tree. It does support a ton of weight. So if we have a pelvic fracture or something shattered within the pelvis, we have concern about this patient walking. We have concern about this patient moving, because again, this is a trunk. It's going to support a lot of the weight of the patient. Our lower extremities, I've got like 2-3 slides left, guys. Hang in with me. We've got our femur, upper leg bone. We've got our kneecap, also called our patella. Our fibula, which is our smaller of the bone, more of our support bone. Our tibia, which is our large prominent bone in our leg that we can feel. We have our ankle, which is also called our tarsal. We have our metatarsals, which runs essentially from our ankle about halfway up our foot, near our toes. And then our toes are considered phalanges. So tarsals, metatarsals, phalanges. Hands, carpals, metacarpals, phalanges. Now, femur, again, is another reason to be concerned if there's blood loss, because we can house 1 to 2,000 liters of blood, 1 to 2,000 milliliters, sorry, of blood. That's a problem when the average adult only holds 5 to 6. I do not expect you to know every single one of these muscles or every single one of these heads or every single one of these fibrous bands. No. All right, last slide. So has anybody in here ever ruptured their Achilles tendon by chance? I know I asked that during another class, but has anybody in here ever ruptured theirs or ripped theirs or torn it? What happens if somebody tears or ruptures their Achilles tendon? Can they technically bear weight on that leg then?
No.
No, absolutely not. It's that long rubber band which gives them the ability to put pressure down on their foot for it to act as a joint. Again, toes, phalanges, from toes to about the arch of your foot is your metatarsals. And then up to your ankle would be your tarsal. All right, I'm going to stop there because we jump into another whole nother system, which is our musculoskeletal system. So our muscles, which we are going to break into next week. Next week is going to be about the same amount of time. We've got roughly 100 slides to cover next week. We covered 94 tonight. So about the same amount of time, but it's gonna go a little bit quicker because we're not talking about cells or anything. What questions can I answer for you guys? I know some of this stuff might be stuff you already knew, which is fine. It might be a review. But there are worksheets on Canvas in regards to the skeletal system. Please make sure you get those labeling worksheets done and email them to me when you are complete. For you guys in Clinton, I'm gonna set up a time to go through Zoom with you and how you should as we start going into scenarios, how you should document those scenarios. And then I'll do the same thing for those of you in Mason City. But what other questions can I answer for you guys? All right, if you guys don't have any questions, you are free to go. I'll post this recording up. If you have questions, please get a hold of me on Teams, shoot me an email. I'll answer any questions that I can. If I do not answer that clinical phone, if you call it, leave a message or leave a voicemail, because I'm probably teaching, or unless it's early in the morning or late at night, I might not be able to answer it either, or I might be sleeping or whatever it might be. But please leave a voicemail. I do check them. And if you guys have any questions about anything, you know how to get a hold of me, and I'll try to help you as best as possible. Otherwise, have a good night, guys.
Hey, Rudy, I do have a quick question if you're still there.
Yep, I'm here.
So this is off topic, but I'm supposed to recertify my license this year. And with me being a student,
Yep,
I would assume this is all of the hours I need.
yep.
Is there a certain piece of paper that I need to send you guys to have you fill out, or is there something I need to fill out, or can I just say
Is it your national or your state? Or
just
both?
my state?
Okay, basically, I can just send you, or actually the syllabus that's on Canvas
Mm-hmm.
for whatever classes, for like mine and John's classes, you can use that as your, your attachment to upload for your state. And then any classes that we've had, you can count as your hours.
Oh, perfect.
And if they have any questions, then they would reach out to us at the college and we would verify it.
Okay.
But yeah, if you have any,
Thank you very much.
let me know.
All right. Thank you.
Yep. Hey, Andrew, are you still there?
Yeah.
All right, let me stop.